Hello and welcome. Today we're going to solve a differential equation with Laplace transforms. So let's get going. Let's start with this differential equation. X double prime plus 4 times x is equal to sine of 3t. So this is a model for a mass spring system. We have a mass, it's going to be equal to 1, maybe kilograms, and it's going to be on a little track like this with a spring attached to an anchor. And on top of that, what we're going to do is we're going to apply a forcing to it, F of t, which is going to be equal to the sinusoidal forcing, like that, where the 3 in this case is the is radians per second, maybe if we're doing this in seconds, and that's the forcing frequency. Okay, so that's the forcing frequency, and x of t then is the motion of that mass, and here the spring constant in this case is 4. Another thing to note here is there is no damping. So we're assuming essentially that there is no friction in the system at all, and there's certainly no shock absorber or any system that would be able to dissipate energy when the thing speeds up. So we can look at the characteristic equation of this system and note that r squared plus 4 is equal to 0 yields plus or minus 2i for our characteristic roots. So my complementary solution is going to look like c1 cosine 2t plus c2 sine 2t. All right, so 2 is going to be the intrinsic oscillating frequency, 2 radians per second. And of course, that is not equal to 3 radians per second. So there's going to be no resonance. Okay, there's going to be no resonance phenomena where, because there's no friction in the system, if there were a resonance, if you were forcing exactly at a resonant frequency, you would end up with an infinite amplitude as time goes further and further forward. But we don't have that issue. And the next thing we need to do is just write down the initial condition. So in this particular case, we're just going to take x and its velocity. Its position and velocity are both going to be 0. And that makes it simple. Okay. So with that out of the way, we've got a general system here. We've got a general feel for what's going on. Now we're going to take the Laplace transform of x double prime plus 4x equals sine 3t. We can take the Laplace transform of all of that and it becomes s times x, the Laplace transform, 4 times capital X again, equals, and then we're going to have a 3 all over s squared plus 3 squared, which is 9. Okay, we can solve for capital X of s, and it's going to be 3 all over s squared plus 4. And that's by just factoring the capital X out, and then s squared plus 9 having to do with the forcing. Right, so that's our answer for this. But now, of course, we need to find x of t then is going to be the inverse Laplace transform of capital X. All right, and the question then is, what is that? And so we're going to have to use partial fractions to solve. Okay, so this looks pretty good. We have to solve this using partial fractions, so let's get to the next page here and we'll work that out. Okay, so again, we want to compute this. The inverse Laplace transform of 3 over s squared plus 4 times s squared plus 3. Or sorry, plus 9 there. Okay, all right. In order to do that, though, this is we don't have a transform on the table, the transform table that looks like this. But we can see here that if we actually break it up into terms, so what we're going to do is we're going to break up into terms with the irreducible quadratics. The irreducible quadratics separated. So you're probably wondering, what does it mean to be an irreducible quadratic? And again, it's something like this: s squared plus 4. I want to factor that. I would like to reduce it to some binomial factors: s plus a, s plus b. If it's irreducible, it means they're not real, right? So a and b are not real, and we know that's true. In fact, if you factor this, if you want to factor it into two binomial factors, it's going to be plus 2i and minus 2i. Okay, so of course those are not real. Okay, so that's what we call an irreducible quadratic. It can't be factored into binomial factors that are real, but we certainly should be able to use the partial fractions on this. So in fact we will. What we're going to do is write 3 over s squared plus 4 times s squared plus 9, and that's going to equal as plus b all over s squared plus 4. So when you have irreducible quadratics, this is the formula in the partial fractions technique, and then you have a cs plus d sitting right there, and that's going to be an s squared plus 9. All right, so obviously this is true for every s. Okay, so it has to be true for particular s values. Okay. So if it's true for particular s values, then we can pick a few. So for instance, I can go s is equal to 0. Before I do that though, I can multiply through by this whole thing and get 3. I'm going to multiply through everything by that, and we're going to get an as plus b times s squared plus 9 plus cs plus d all times s squared plus 4. Okay, and if I take s equals 0, I can plug it in there and get a b times 10 plus d times 4, like that, right? Oh, whoops, that's not right. Make one mistake. It's not 10 there. It's going to be 9. Okay, very good. And that has to equal 3. I can solve now. B is actually going to be 3 minus 4 times d all over 9, and this is going to be 3/9, so that's going to be equal to 1/3 plus 4/9 times d. Okay, and of course what I'd have to do is solve for a couple more values like that to get 4 equations, and then 4 unknowns. 4 unknowns. Okay, so these equations and 4 unknowns, that's going to be complicated. What we want to do now is ask ourselves if we want to continue down this path. It definitely would work. It will work. But again, it'll be complicated. You're probably going to want to use a computer. Otherwise, you're going to spend the next 10 minutes with me, maybe 15 minutes, solving this thing. But we don't want to do that. Instead, I'm going to save you the trouble. We'll just actually write down what the answer is. Okay, so it turns out, once you do all the calculations, you're going to find out that A is equal to 0 and C is equal to 0. But B is going to be equal to 3/5, and D is going to be equal to negative 3/5. Okay. We can do the math to figure that out if you want, but those are the answers, and that just saves us time. So let's write down what the thing is now. So now we have 3 is equal to 3 over s squared plus 4, s squared plus 9. All of that is equal to, we can write it down as 3/5 all over s squared plus 4 plus negative 3/5 all over s squared plus 9. Okay, so remember that is capital X of s. Right, so if I take an inverse Laplace transform of capital X of s, that's going to equal x of t, just like we want, and that's going to be the inverse Laplace transform of all this stuff in there. But because the Laplace transform and the inverse Laplace transform are linear, we can actually say that that's going to be 3/5 inverse Laplace transform of 1 over s squared plus 4 plus inverse, I should actually say not plus, but minus 3/5 times the inverse Laplace transform of 1 over s squared plus 9. Okay, so we're certainly getting close. Again, that is my x of t. I want to find what it is. But we know the inverse Laplace transform of omega over s squared plus omega squared is equal to sine omega t. All right, so if that's, we're always trying to essentially take our inverse Laplace transforms and see if we can match them up with some fact we know in order to follow our way back to get to x of t. And we see what we have to do is actually, we're going to now multiply then. I see the 4, that's actually 2 squared. So what I need to do now is multiply this thing by 2 over 2, like that. And here, I'm going to need to multiply everything by 3 over 3. I see actually I have a 3 right there. So I'm just actually move it back in. So we're going to get this. We're going to get 3/10 inverse Laplace transform of 2 over s squared plus 4. And the idea here is this 2 is going to distribute back inside Laplace transform because Laplace transforms and inverse Laplace transforms are linear. Minus 1/5 inverse Laplace transform of 3 over s squared plus 9. All right, now we got everything in the form. We know exactly what that is. That's going to be 3/10 times sine 2 times t. Okay, cool. And then finally, that's going to be minus 1/5 times sine 3t. Very cool. That will be our answer right there. So that is my x of t. I found a solution. And again, the goal was we had to use partial fractions in order to get our answer, right? And solve all those constants. That was probably the hardest bit of work. You'd have to go to a computer or solve that linear system. And then also match up the terms that you find from that with things that you know how to take the inverse Laplace transforms of. Okay, so that gives me the answer. I hope this is a good example, and we'll do more in the future. Thank you very much.